Welcome to the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series begun in the spring of 2020 and then restarted last autumn has been an immense success, and the recordings of those webinars continue to be viewed on YouTube. We plan to continue these webinars through the present academic year with a variety of speakers from industry, academia, and other research institutions, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Yoshiaki Kawajiri of Nagoya University. I'm Daniel Sidarius of NIST in the United States, and I'm the Secretary Treasurer of the IAS. Today's webinar will be moderated by David Donacci of Imperial College London in the UK. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or of the institutions associated with those individuals. We ask that any viewers who are not already members consider joining the IAS as a regular member. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter with our handle @intadsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. We'd also like to announce and remind everyone about our upcoming Fundamentals of Adsorption meeting, the 14th edition, which will be held in May of 2022 in Broomfield, Colorado, just northwest of Denver. We'll be covering a variety of topics relevant to gas phase, liquid phase, adsorption, molecular simulations, development of adsorbent materials, and a special focus on environmental and energy applications of adsorption, both for remediation and generation purposes. And here we have a view of the golf course that's at the hotel in Broomfield, overlooking the Boulder Flatiron Mountains, which will be a wonderful setting for the FOA meeting. And now I'd like to hand over the narration to David Donacci to introduce our speaker.
Thank you, Dan. It is my pleasure to introduce Professor Yoshiaki Kawajiri, who is a professor at the Department of Materials Process Engineering at Nagoya University in Japan. Professor Kawajiri completed his bachelor's and master's degrees at Kansai University in Japan and joined Organo Corporation in 1999. He obtained his PhD in chemical engineering at Carnegie Mellon University in the US in 2007. After completing his postdoctoral study at the Max Planck Institute in Magdeburg, Germany, he became an assistant professor, and he was associate professor at Georgia Tech with tenure from 2008 until 2017. His research interests are process modeling and optimization of adsorption processes. During the webinar, questions can be submitted to the speaker via the Q&A tab in Zoom or as comments on YouTube. Those comments will then be forwarded to the hosts on Zoom. With that, thank you very much, and please, Yoshi, take it away.
Okay, thank you for the introduction. Do you see my screen?
Yes.
Okay. And the title of my talk today is Bayesian Approaches for Adsorption, Isotherm, and Process Modeling. So I recently moved from the United States to Japan, as David introduced. And I was an assistant and associate professor at Georgia Tech in the US until 2017. And since 2017, I came back to Japan, and I'm at Nagoya University. My talk is about modeling for adsorption process. Since I'm a process engineer, my presentation will be from the viewpoint of engineers. Now, the process engineer's objectives is to design separation process that achieves many goals, such as high throughput or productivity, high purity, high recovery, but at low energy usage. And to design such a process, predicting the process performance is critical. And usually we use a mathematical model with an aid of computers. To predict the performance of processes, statistics and data science can be a powerful tool. So it is a common misunderstanding that the data science is always about big data, but that is not the case. There are many advanced techniques in data science for small amount of data. And in the research community of adsorption, we usually deal with a small amount of data. And that is also the case for my talk today. So in the disciplines of data science, statistics plays an important role. Here's an outline of my talk. I'm going to talk about 2 parts. The objective is to utilize statistical techniques to adsorption. The first part is about isotherm modeling, and the second part is about adsorption process modeling, and with some examples of chromatography. So let me start with part 1, statistical techniques for adsorption process modeling. I assume many of you are already familiar with isotherms, and an isotherm describes the equilibrium between adsorbent and adsorbate. So this is a figure that I took from this paper, which is on IUPAC classification. The horizontal axis is the relative pressure or partial pressure or concentration, and the vertical axis is the amount adsorbed on the adsorbent. And depending on the combination of adsorbent and adsorbate, there's a variety of relationships between the pressure and the amount adsorbed. So let me discuss isotherm models. To predict the performance of an adsorption process, we need a mathematical model. We need to predict the equilibrium relationships. And here, instead of partial pressure, I use concentration C in these equations. And if you look at some literature, you can find many different types of isotherms, from simple ones to very complex ones. Probably the simplest one is Henry's law, which includes only one parameter, H, or Henry's constant. And there are also 2 parameter models, the well-known Langmuir isotherm, which includes 2 parameters, Q sat and B, and Freundlich isotherm, K and N, and Temkin, B and A. And also there are 3 parameter models, such as TOF, Q sat, B and N, SIPS, and Henry Langmuir isotherms. And there are also many other types of isotherm, which includes even a larger number of parameters, such as bi-Langmuir and so on. And I cannot cover all possible isotherms. In addition to these parameters, some parameters may have temperature dependence, which can be modeled by the Van't Hoff equation, or maybe simpler linear relationship. Among many model candidates, you need to determine which model to use. And after determining which one to use, you need to determine all parameters, which are shown in red. And that requires a lot of effort. So these problems can be addressed, at least partially, by some conventional statistical techniques. Suppose you plot experimental data on this plane of C and Q, and you want to fit the data to the model. And you want to fit the right model that fits all data. And in this talk, I will always use the symbol theta to describe the parameters. And in this problem, here are 2 different viewpoints. The first is the model fitting, or how well the model fits the data. This is commonly done by many researchers. And this can be done by root mean square deviation, or RMSD, or alternatively, coefficient of determination, or R squared values. On the other hand, the other viewpoint, parameter uncertainty analysis, this is often overlooked. After determining the parameters, you may want to check the accuracy and precision of your parameters. Otherwise, your model cannot be trusted to predict equilibria under unknown conditions. There are many techniques, such as confidence intervals or confidence region, bootstrap, and sampling. And I'm going to look at an example. Suppose we want to model CO2 adsorption isotherm on amine functionalized silica gel, and we obtain isotherm data, and we plot partial pressure on the horizontal axis and the amount adsorbed on the vertical axis at different pressure and temperature. And we want to model this to an isotherm. So let's say total isotherm, and we need to determine the parameters included in the model, which are QM0, eta, A, B, B0, and delta H. And we call the parameter vector as theta. So the next step is to determine these parameters. So I'm going to look at two different approaches for determining the parameters. One is regression, the other is sampling. Let me talk about regression first. This is a more common approach where you minimize the distance between the data and the model. And you want to find the parameter theta that gives the best fit to the model. So we look at this first. So we carry out regression. So we minimize the distance between the data and the model, and we determine these parameters. So when you solve this optimization problem, you get set of lines for the data, and you can determine these parameters. And this is commonly done, but you don't know how much you can trust these parameters. You don't know how accurate or how precise these parameters can be. To answer this question, so let me introduce the concept of probability distributions. Accuracy and precision of parameters can be quantified by probability distributions. If you have only one parameter in the model, the probability distribution can be plotted as a one-dimensional plot. The horizontal axis is a value of the parameter, and the vertical axis is a probability density. And the value of the parameter theta is most likely here, but it can be here or here, but at the lower probability. If you have more than one parameter, then the plot becomes multidimensional. Suppose there are two parameters, theta 1 and theta 2, then your plot becomes two-dimensional. And the parameters estimated with high probability can be represented by sharp profile. The value of the parameter is very likely to be here, and there's not much room. On the other hand, parameters which are estimated with low precision is represented by broad probability distributions. And in the two-dimensional plot, the parameter can be anywhere in this large region. So the probability distributions, this concept is handled within the framework of statistics. And in statistics, there are two major schools. One is frequentist, and the other is Bayesian. The frequentist assumes that the probability is frequency, and the parameters are unknown but fixed, and it does not utilize prior information, and it's relatively easy to compute. On the other hand, there has been substantial advance in Bayesian approaches in recent years. It treats probability as belief, expectation, or knowledge, and it assumes that the parameters are unknown and uncertain. And it utilizes prior knowledge, which I'm going to discuss later. And the computation, it tends to be computation intensive. The computational burden has been resolved by the availability of increasing computational power today, and that assisted the advance of Bayesian approach. So the Base Theorem is a very simple mathematical equation. It says the probability P of theta y, P of theta, the parameter, given the data y, is proportional to the probability of y given theta times P of theta. And let me give you an illustration here. So in this illustration, the P of theta is called prior distribution. This represents your prior knowledge. And P of y given theta, this is called likelihood function. This represents the information from the data you take. And the Base Theorem says that by using these two probability distribution, you obtain posterior distribution, which is a probability of the parameter theta given a data set y. So here's another illustration. Suppose you have a model, let's say Toth isotherm, and you need to determine the parameters in the model, which are shown in red. And to determine the parameters, you obtain the experimental data. And in addition, you need prior distributions, which is your prior knowledge. By applying Base Theorem, you obtain posterior distribution, which gives sharper probability distribution, which means that the parameter estimation can be improved by the data. So let me talk about prior distribution. So prior distribution in Base Theorem is your prior information, such as literature value, empirical knowledge, and so on. And you can express the prior information, such as normal distribution or uniform distribution. For example, you may know that the value of heat of adsorption, delta H, was previously reported to be around 30 kilojoules per mole. Such information or expectation or belief can be represented well by the normal distribution. So the 30 kilojoules per mole is the center of this distribution. And it may deviate to some extent. And similarly, you may have some lowest possible value and highest possible value. And in such a case, uniform distribution could be the right representation for your prior information. For example, from your experience, the saturation capacity QSAT wouldn't be as low as 0.1 mole per kilogram, but it wouldn't exceed 10 mole per kilogram. Such information or knowledge can be described by the uniform distribution, where the lowest possible value is the lower bound and the highest possible value is the upper bound. So that's prior distribution. So with Base Theorem, we can apply an alternative approach to regression, which is sampling. This approach is simpler in one sense. You simply evaluate the model at many different values of theta. Then you can construct the probability distribution from the sampling. So let's look at the example I have just shown. So we solve the same problem, but this time applying Base Theorem and sampling. So we have data, and we call this y. And we apply, we also use prior distribution, which is your prior knowledge. And this time we apply the uniform distribution. And with these two pieces of information, we apply the sampling technique, which is called Markov chain Monte Carlo approach. By applying the Base Theorem and this computation technique, you obtain probability distributions of these parameters. So in these probability distributions, for example, we look at the heat of adsorption, delta H. And this time we learned that the heat of adsorption is most likely at 90 kilojoules per mole here, but it can be as low as 40 kilojoules per mole, but it can be as high as 140 kilojoules per mole, but these are at a lower probability. So that's new information you get. So let me briefly discuss the numerical approach that I talked about, MCMC. So the Markov chain Monte Carlo, or MCMC, suppose you have data, let's say it's plotted on the X and Y plane, and you evaluate a model, let's say f of x, at two different set of parameters, theta 1 and theta 2, at two different values, this blue set of values and red set of values, which are represented by these two vectors. And you notice that these blue values fit the data well. So you accept this blue step. And by accepting these better fitting steps, you keep approximating these probability distributions. And by repeating this approximation and taking these random steps, we obtain the probability distributions at the end. So that's MCMC method. So I only talked about the Toth isotherm, but selection of the model could be sometimes very difficult. Then let me talk about isotherm model selection. Suppose you have experimental data, your isotherm experimental data, and you need to decide what model should describe the data. And as we have seen, there are many model candidates which have different models, different numbers of parameters. For example, the Langmuir isotherm has only 3 parameters, but the Toth isotherm may include a larger number of parameters, and it's not easy to decide which one is the right choice. This problem is called a model selection problem. This is a very common problem in statistics. And this is a generalized plot where you have data on the X and Y plane. And if you use a more complex model with a larger number of parameters, you may get a better fit. But getting a good fit is not your objective. Your objective is prediction. You want to predict the equilibrium at unknown conditions. So for this problem, I'm going to introduce the concept of overfitting. So in overfitting, the model fits the data too closely, which means that the model adjusts to the deviations caused by experimental error. So we need to find a good fit, but at the same time, you need to avoid overfitting. So that's a difficult problem, but there are some techniques in statistics. And I'm going to show some techniques. And today, I'm going to show only 2 techniques. One is cross-validation, and the other is information criteria. So let me talk about the first technique, cross-validation. In cross-validation, you test the predicted performance of the model directly. Suppose you fit the model without this red point. You leave out one data and fit the model. Then you compare the model with the unused data, this red point, and see which model fits the best. Then in cross-validation, you repeat this process by choosing another point. This time you leave another point and fit the model with the rest of the model. And check the data point, which is left out. Then we change the data point and repeat this process. And this is called cross-validation. You rotate through all experimental data. And let me talk about another approach, which is called information criteria. This equation is called Akaiken information criterion, or AIC. And this equation is given by 2 times number of parameters, subtracting the maximum value of likelihood function. This represents the goodness of the fit. It considers the trade-off between the number of parameters and the goodness of the fit. This AIC, this can be derived theoretically under some assumptions. It finds the best model in the trade-off between the model complexity for a number of parameters and the model fit. It finds the right balance between the 2 conflicting objectives. So we look at the same problem again, the isotherm problem, and apply the information criteria. The information criteria were evaluated for these 3 different models that I have shown. Among these 3 models, the 5-parameter model in the middle, this gives the lowest value of AIC, which means that the AIC indicates that this is the most appropriate model. I am also showing BIC, which is a very similar concept to AIC. So we can determine that this is AIC gives tells you that this is the right choice. Let me discuss another problem, and that is Bayesian design of experiments. The question that we want to answer is that we want to find the optimal experimental conditions, temperature and pressure, to reduce the parameter uncertainty. And this question can be answered theoretically by considering the maximized information gain. By evaluating this utility function that evaluates the information gain, the optimal temperature and pressure can be determined. And these are plots of probability distributions where data are added, which were taken at the optimal temperature and pressure. The probability distribution gets sharper and sharper as more and more data are obtained at the optimal temperature and pressure. So far in my talk, I have never discussed how to obtain the data. And let me talk about finding isotherm data from a database. And there was a webinar on the NIST database by Daniel a few weeks ago, and we can find a lot of data from this database. Our research group has been using this database in the last several years. So let's think about using this database. But if we want to use this database for modeling, there are some problems to be solved. First, the experimental conditions in the database may not be consistent. This is an example of CO2 adsorption onto UIO 66, which is a metal organic framework. As you can see, the different temperature and pressure were chosen by different researchers. When you use these data to model, we need to decide if we should use some of the data by selecting them, or we should use all data at once. And suppose we want to use as much data as possible for your modeling, then we encounter another problem. The second problem is that even at the same condition, the data are not necessarily consistent. And this is a plot for the same material taken at the same pressure and temperature. And as you can see, the reported value is not always consistent. Unfortunately, I'm not an expert of adsorption materials, and I'm unable to discuss what is going on. Some potential reasons include the differences in the measurement, or maybe in the experimental protocol, or maybe material synthesis and preparation. And I can't figure out which one caused the problem. Since I'm not an expert, all I can do is just to quantify the differences. So suppose we want to model these sets of data to a single set of isotherm with a single set of common parameters. To this model, we multiply a coefficient Ri, which is given for each researcher. I goes from 1, 2, and 3. So we determine the common parameters and individual parameters simultaneously. So in this approach, we analyze the data I have just shown. This concept is available in Bayesian statistics. This is called hierarchical Bayesian estimation. So we collected data from 11 researchers from the NIST database, and we applied the same approach using the modeling approach that I discussed, where we have individual coefficient Ri multiplied for each researcher. And by this analysis, first we obtain common set of parameters, which are common for all researchers, Qs, B0, and delta H. And in addition, simultaneously, we obtain individual coefficient Ri for each researcher. By looking at this distribution, we identify some researchers which are in agreement with each other, where the value of Ri is close to 1. On the other hand, we can also identify outliers where the reported adsorption amount is significantly lower than other researchers. So this is called hierarchical Bayesian estimation. we can include molecular simulation data in this analysis. And we can use such a data set as a reference point. The data set is a CO2 absorption on 0 at 13x from this database. And here are the data sets. And in addition, there's one set of molecular simulation obtained by GCMC. And we use this data set as a reference point. And we quantify the deviation from molecular simulation. Researchers 3, 4, and 5, as you can see, they reported close values. The values of Ri is close to 1.0, which means that these researchers reported experimental outcomes are close to the molecular simulation. On the other hand, researchers 1 and 2, the data are somewhat away from the molecular simulation data. So here's a summary for part 1. I introduced the concept of Bayesian inference, and we have seen the sampling-based method, and we have also seen the design of experiments to reduce the parameter uncertainty. And we have seen hierarchical estimation to quantify the differences in the data set. And let me conclude part 1, and let me take a brief break. And I'm going to take questions at this point. So should I hand over to David, I assume?
Yes, thank you very much, Yoshi. A very interesting part 1, showing all of these statistical methods for model fitting. At the moment, we're just waiting for questions to come through on Zoom and also on YouTube. So if you are watching on YouTube, please submit your questions. While we're waiting for that, I guess I have a quick question to start with. When you're looking at something like the sampling-based method, and you have many parameters, say 6 isotherm parameters, or for the larger models, what is the most convenient way to show the distributions between all of those parameters? Because sometimes it can get a bit messy. Do you have any suggestions for that?
I think your question is about representation of the multi-dimensional parameters.
Correct, yes.
Yeah, good point. So if you have only one parameter that is showing the distribution is easy. But if you have more than 2 parameters, that as a human being, we are unable to understand a multi-dimensional space.
Yes.
Mind. But what you can do is just show them as 2-dimensional plot. And this means that that's a projection of your multi-dimensional space onto the space of 2-dimensional. That's all we can do. And maybe you can plot it as a 3-dimensional plot, and that's possible. But that's all we can do. But that's a good question. I mean, for visualization, it should be either 2-dimensional or 3-dimensional.
Yeah, thank you very much. We are still waiting on a few questions, so I'll ask another one if that's okay, and then we might continue the webinar. In the case, like on the left here, for one-dimensional analysis, you have a nice normal distribution. In some of your slides, you showed that the distribution can be skewed. So it's not really easy to give a kind of mean value and standard deviation. Do you have any suggestions on how to represent or deal with those cases there?
Good point.
Yeah.
For example, if you look at this example, for example, the value of A is skewed, for example, and this log of B0 is also skewed. That's a very good point. So if you try to understand this just by mean, you'll be misguided. The most frequent value is actually away from mean. So what you should do is to look at this distribution, and you need to look at the difference between mean and the most frequent value. Those are two different things. And sometimes the probability becomes multimodal. So you may have 2 peaks, 3 peaks, and so on. And that could be the nature of your estimation problem. And if you try to understand it just by mean or even variance, standard deviation, you may be misguided again. In such a case, you need to look at the distribution by yourself and see what's going on. That's what you should do.
Yeah, thank you very much. Very nice suggestions, and thank you for answering the questions. If it's okay with you, and if you don't mind, we can continue to the next part of the presentation.
Okay. Okay. So let me move on to part 2. I'm going to talk about processes this time. So I will talk about adsorption process design. And again, the objective is to design a process that achieves high throughput, high purity, high recovery, but at a low energy usage. And to achieve these goals, prediction of process performance is critical, and we need a model. The question we want to answer in the second part of my talk is to how to establish the model and how to predict the process performance. And I'm going to use an example of simulated moving bed or SMB chromatography. And here's the steps for process design for SMB chromatography. So we start with injection test using a packed column. And from the data obtained from this experiment, we estimate the model parameters. And using the parameters, we establish the process model. And finally, we carry out model-based process design. And when you design a process, it is critical to predict the performance of the process. In the SMB process, the quality of the product must be predicted, which includes purity and recovery. So suppose these are the probability distributions of the purity and recovery, and which are both important performance metrics. And usually there are requirements for purity and recovery. And we must meet those requirements at sufficiently high probability. So when you are in this relatively large region of probability, your requirement is satisfied. But your requirement may be satisfied at very small percentage. So in this talk, maximize the probability of meeting the requirement. Let me refer to it as a robust design problem. So we start the design problem with pulse injection test. So in this test, the inlet concentration of the column is changed as a pulse. So suppose we have 2 components. The red component is a weakly adsorbing component, and the blue component is a strongly adsorbing component. And we supply this mixture from the inlet of the column. Then it is pushed by the solvent. As these components travel through the columns, they start to separate from each other, and they are detected at the end of the column. And here's a process model for chromatography. And this is more complex than just the isotherm equation that I have shown. There are mass balance equations, which are partial differential equations. In addition, there's also an isotherm, for example, the Langmuir isotherm, to describe the equilibrium between the adsorbent and the components in the liquid. In the model, there are parameters to be estimated, for example, the mass transfer coefficient, Ki, and isotherm parameters, including Henry's constant and equilibrium constants. Even for such a complex model, we can use either of the approaches we have seen previously to determine the parameters. Regression minimizes the distance between the model and the data and determine the parameter data. On the other hand, in the sampling approach, the model is evaluated at many different values of parameter theta. So theta I, where I goes from 1, 2, and 3. And you represent the probability distribution of your parameters. So in part 2 of my talk, I will talk only about the sampling approach. So here's a case study for separation of cyclohexanone C5 and cyclopentanone C6 on an ODS column. Some injection tests were carried out, and here are the results of the single component injections, and here are the injection of the mixture. So first, we collect such data. Again, we analyze this data using the same approach. So by using the same approach, the Markov chain Monte Carlo method, but this time using the process model, which includes a partial differential equation. So this is more complex. So the computation time takes much longer time. But at the end, we can estimate all parameters, including the mass transfer coefficient, K, as well as the isotherm parameters. So we have seen the pulse response test where the inlet concentration is changed as a pulse. And in the example that I have just shown, we carried out multiple experiments to estimate the parameters. And obviously, this is not the only possible test. And there are many alternative experimental techniques for modeling. For example, in breakthrough test or step response test, the inlet concentration is increased in a stepwise manner. And the mixture is kept supplied to the column all the time. And we will also use the data from this experiment simultaneously together with the pulse experiments. Now, here's a result, and we see improvement by combining both kinds of data. For the sake of analysis, we will use only computationally generated artificial data this time. We carry out both pulse and step response tests or breakthrough tests. And these two different types of data are analyzed by the same approach, GCMC, with the same mathematical model. And here's the resulting probability distributions. The red distribution or pink distribution, these are distribution obtained from the pulse response test. And the blue distributions from the step response test. Now, the purple distribution are from the pulse plus step response test together. These are from the combined data sets. And as you can see, the combined data sets gives the more accurate and precise estimate. So combining these data sets can improve your estimation. So actually, this is well known by experts of chromatography, and we can explain this. And the good estimate by using both experiments is because of the difference in the concentration. In pulse response test, the concentration tends to be very low, and the Henry's constant HI can be estimated even at such a low concentration. On the other hand, in step response test, the concentration becomes very high at the end. And as a result, the parameter BI that is multiplied by the concentration CI, that is estimated more easily. So these two different types of tests work in a complementary manner to estimate the different parameters. So that explains the good estimate that we have seen. Let me show you another test. So this is an alternative technique. That's a stair-step injection, where the inlet concentration is changed in a staircase profile. This test is also often performed by experts of chromatography. And if you look at the results, we see that all parameters were also obtained sufficiently accurately. So this means that only a single set of data is sufficient this time. This injection strategy is already known by experts of chromatography, somewhat empirically and qualitatively, but we can quantify the advantage using the statistical techniques. So the number of stages in the injection can be optimized. We consider 2-stage input, 3-stage input, or 4-stage input. And we apply the same analysis, and here are the results. The white profile is a 2-stage input. And as you can see, this white profile is the broadest. On the other hand, this 3-stage input, pink, and 4-stage input, blue, they give a sharper profile, but you wouldn't notice much difference between 3-stage and 4-stage. So this means that probably the 3-stage input is sufficient, and increasing the steps further into a larger number of steps is probably not necessary. So I'd like to point out an important analysis called parameter correlations. Suppose we have 2 parameters, theta 1 and theta 2. And here are the plots for weak and strong correlations. When there's a strong correlation, any combination of theta 1 and theta 2 along this line gives nearly the same fitting. And in such a situation, determining a unique set of theta 1 and theta 2 becomes more difficult, because any combination along this line gives you nearly the same fit. So we see that this problem also happened for our problem too. Here's a correlation analysis for all pairs in the parameters in our model. So we notice that there's a strong correlation between these pairs of parameters, which are BC5 and HC5, and HC6 and BC6. And for example, these 2 parameters, BC5 and HC5, these 2 parameters appear in the same equation of isotherm. So HC5 is multiplied to the same variable, CC5. And similarly, this combination of HC5 and BC5, the combination of these parameters also appear in the same equation. And that explains the strong correlation between these two parameters. So in order to resolve these correlations, more variations in experimental data is needed, and we may need to spend more experimental effort. So let me go back to the problem of robust process design utilizing statistical techniques. We have so far seen that a single injection test can be carried out, either pulse response test or step response test or staircase input. And we can carry out model parameter uncertainty. And by using this model uncertainty and mathematical model, we design a process. Then we can quantify the uncertainty in the process performance, such as purity and recovery. And here the plot of probability distributions of purity and recovery. And we want to make sure that the required purity and recovery are obtained at sufficiently high probability. And that is a robust design we pursue. And that can be assisted by the statistical techniques that I have just introduced today. And finally, let me discuss some alternative computation methods. It is crucial to reduce the computation time. In this talk, MCMC or Markov chain Monte Carlo method was discussed, but the application to process model can be very computationally intensive. In the example that I have just shown, there were cases where the computation took more than several days. So on the other hand, there are some techniques to reduce the computation effort. For example, sequential Monte Carlo method with likelihood tempering. In this technique, the likelihood function is divided and applied successfully. And in this technique, this computation can be implemented on a multiple CPU core as parallel computing. And we confirmed that the CPU time can be reduced by distributing the computational effort to multiple CPU cores. And I would like to conclude my talk with a famous quotation. George Box said that all models are wrong, but some are useful, which indicates that all models are just approximation. And I'd like to focus on this part, useful. So this means that all models must have objective. The question is that if our models are useful for our objective or not. For process engineers, the objective is to design and develop adsorption processes, which achieves high throughput, high productivity, high purity, high recovery, but at low energy usage. So the Isotherm models and process models that I have shown today, these are just approximations, but they should be useful when you design and develop adsorption processes. So here's a summary for part 2. We have seen that the sampling method can be applied also to the process model to quantify the uncertainty in the process. And the quantified uncertainty can be applied to design process with robust process design. I was asked to give 5 references. So let me start with a list of introductory books. Montgomery is an excellent undergraduate level statistics, and Hoff is a good graduate level textbook for Bayesian statistics. And for absorption and chromatography processes, and these are my favorite books. And in addition, here's a list of related work, which were very useful for our own research. And many of them are from the research committee of absorption. And sorry, I can't show all of them, but these are just examples. But they are very useful for our research. And let me acknowledge my former group members at Georgia Tech and my current group members at Nagoya University. And I was fortunate to work with many collaborators. They were my colleague, my current collaborators at Georgia Tech, and my former PhD student, Jayashree Kalyanaraman. I learned Bayesian statistics from her. What I showed today were also done with my colleagues and students at Nagoya. And thank you for your attention, and I'll be happy to answer your questions.
Thanks again, Yoshi. A very, very interesting part 2, especially the process design uncertainty. So I'm just waiting for some questions to come through if there are any. So if you do have questions, please post them in the Zoom Q&A tab or on YouTube. There is a question from YouTube. A question from Greg Chung in Busan, Korea. It is very interesting that the RI values could match with molecular simulation data. What can we learn from the experimental data when the RI matches with molecular simulation? So I guess this is talking about part 1 of your talk.
Okay, thank you. Let me go back to the slide. Just 1 second. Okay. And thank you for your question. We also noticed that some papers, the data given by some papers are very close to the molecular simulation, and some are not. And as a non-expert, experimentally, I don't know what is going on. All I can say is that their experiments and material preparation is probably close to ideal. So the non-ideality, if the value is away from 1.0, which would probably mean that there are so many defects, or maybe the activation wasn't sufficient, or maybe something went wrong in the measurement. I don't know as a non-expert. So experimentally, I don't know what is going on. So as a non-expert, but as from the viewpoint of statistics, what I can say is that their condition, their experiments was very close to the ideal condition of molecular simulation. That's all I can say. sorry, I can't give you much insight, but I hope there's someone who's more familiar with experimental techniques can answer this question. But I don't know. But this is still a preliminary work, and I hope to publish soon so that we can get more opinion from experimentalists.
Thank you very much. We have another question from Arvind Rajendran, who is referring to in part 2 the probability distributions for the process design. And his question is, in the chromatography examples, the probability distributions indicated that the purity and recovery values fell within a very small band, so similar to the experimental precision. The first question is, what does this tell us about the system? And the second question is, are there any situations where this may not be the case?
Thank you for the question. Let me go to the slide. Okay, first of all, I think you read these numbers, and I think I'm right. These are too small. So I agree with you. So the reason is that this is just a computation experiment. So we obtained these data computationally. So we did simulation, assuming some error, and the error was analyzed and propagated through the SMB model. And as a result, the resulting variation was very small. So this means that our simulated data or artificial data could be too ideal. The error was too small. So we are looking at this problem again. So maybe we may need to look at a greater deal of error in the assumption. And the another point to answer your question is that in this analysis, we didn't consider any other non-ideality other than the parameter uncertainty, such as dead volume or flow maldistribution or fluctuation of flow and so on. These are not considered in this analysis. So if you consider those uncertainty, this width would be much, much broader. So all I can say is that in this computation experiment, the variation is low. But if you need to think about some other non-idealities concerning flows, packing, and dead volume, and so on, this probably this probability would be much, much greater. I hope I answered the question.
Thank you very much. Yeah, well, I guess we'll see if Arvind has any follow-ups. I have a quick follow-up about this slide as well, and it might be in terms of the time we have, perhaps the last question. Do you have any comments or insight as to how the kind of energy consumption, of especially the productivity, has changed, in this distribution as well? So it seems the purity and the recovery is quite a narrow band. Does the productivity also stay quite narrow?
First of all, there are two ways to answer your question. Suppose the first way to answer a question is that once you fix the design, your productivity and energy usage is fixed. So there's nothing you can do. There's no uncertainty once you fix the design and operation. Okay. The second way to answer your question is that suppose you fix your design and operation, and suppose your probability distribution or purity and recovery is not what you expected. So suppose it's too low or too broad. In such a case, you need to go back to the design and you need to readjust the design. In such a case, your productivity would decrease. And as a result, your productivity could be decreased. So let me summarize my two ways to answer the question. First, if you fix your design, your productivity is also fixed, but that may not be the right way to go. So what you need to go back to your design and redesign your process. If that's the case, your productivity may suffer. And as a result, there could be some uncertainty in the productivity and also for energy usage. So it's difficult to answer your question. That's a very good point. And there are two approaches.
Yeah, thank you very much. I guess the flow rates and the switching times are fixed in this example, and you're just looking at the impact of the parameter estimation uncertainty.
Good.
Right. Thank you very much. We have another question from YouTube from Isabel H. From Max Planck Institute, Magdeburg. Thank you for this interesting talk. Does your Bayesian approaches help to determine the sensitivity of your model parameters towards certain experimental data or parameters?
Very good point. Thank you for your question. So let me go back to the slide that where I can answer a question. The short answer is yes. So you want to find the sensitivity, and the sensitivity can be. Let me go back to the slide for this. So let's say, in this example, suppose the resulting parameter distribution is broad. Then that means that the sensitivity is low. That would in that way, you would know that each parameter is sensitive or not. So that's one way to deal with it, to find your sensitivity. But you also want to make sure that the sensitivity is high enough. Ideally, the sensitivity should be high. So you can find such experimental condition which gives high sensitivity. That is given by design of experiments that I just talked about. So I briefly talked about Bayesian design of experiments, which gives the optimal experimental condition of temperature and pressure. To rephrase this optimal experimental condition, this gives the condition that gives the highest sensitivity. You can maximize the sensitivity to sharpen those probability distributions. So I hope I answered the question. One is that yes, you can find sensitivity. And second, by using Bayesian approach, you can maximize or you can increase your sensitivity by carefully choosing experimental conditions.
Thank you very much, Yoshi. That appears to be all the questions that have come through. And again, thanks for taking the time today to give this nice presentation. With that, I will hand back over to Dan Siderius, who will give some final comments and wrap up today's session.
Thank you, David. And also thank you, Yoshi, for your presentation on the application of Bayesian methods to modeling adsorption processes. I'd like to thank our attendees for joining this webinar, and we hope that it was both educational and enjoyable. An edited version of this webinar will be posted on IAS's YouTube channel shortly, and then we'll also announce that on IAS's Twitter feed. The hope is that this work discussed today will be a useful resource for the adsorption science community in the future. We're going to pause our webinar series for July and August. We're going to resume in September 2021, starting with a presentation by Professor Hideki Tanaka of Shinshu University in Japan. The exact date will be announced on the IAS Twitter feed and through the mailing list. We hope that you'll join us. It's possible that we'll have some other IAS online events this summer, so just stay tuned to the Twitter feed and the mailing list, and we hope that you can join us for any of those events. With that, we hope that you have a good Monday, that you start your week well, and we will see you soon. Thank you and goodbye.